In May of 1935, Albert Einstein wrote a letter to Erwin Schrödinger, complaining that the most important argument he had ever made about the nature of reality had been buried under formalism by a co-author he had not chosen. The argument was about whether quantum mechanics is the complete description of the world or whether something deeper lies beneath, and Einstein believed the answer had to be something deeper. 47 years later, in a basement laboratory in Orsay, France, an experiment finally settled the argument. Einstein lost. The universe is not locally real. The measurement was 40 standard deviations beyond the threshold local realism was supposed to obey. The man who proved the theorem died 2 years before he would have received the Nobel for it. The first experimentalist to confirm it was thrown out of Richard Feynman's office. So what did the universe actually answer when physics finally bothered to ask? Make yourself comfortable. Subscribe if you have not already. Stay with us because the answer leaves you standing in front of 4 doors and there is no 5th door, and one of them is open right now under your hand. Let's begin. Part 1. The Quiet War in Princeton. In May of 1935, in a Princeton office heavy with cigarette smoke and the smell of paper, a 56-year-old man sat at his desk and wrote a letter to his closest friend in physics. He was angry. Not the loud, performative anger of a young man trying to make a point in a faculty meeting. The cold, mathematical anger of a person who had spent a decade watching a theory he helped create being interpreted in a way he believed was philosophically monstrous. The man was Albert Einstein. The theory was quantum mechanics. The letter was to Erwin Schrödinger, dated June 19, 1935. In it, Einstein complained that the essential point of the argument he had just published had been smothered by the formalism. The argument was simple in shape, but it touched everything. Einstein had spent the last decade trying to defeat quantum mechanics from the outside through clever thought experiments designed to break the uncertainty principle. He had lost those rounds. Niels Bohr had stayed up entire nights at the Solvay conferences of 1927 and 1930, constructing counter-arguments that even Einstein in the end had to concede were correct. By 1935, Einstein was no longer trying to break the theory. He was trying to show that it was incomplete from within. He had written a paper with Boris Podolsky and Nathan Rosen called Can Quantum Mechanical Description of Physical Reality Be Considered Complete? The paper appeared in Physical Review, Volume 47, page 777. The physics community has known it ever since as the EPR paper. The argument took the form of a criterion. If, without disturbing a system in any way, you can predict with certainty the value of a physical quantity, then there exists an element of physical reality corresponding to that quantity. In plain language, if you can predict what a measurement will give you, without touching anything, then the thing you predicted must have been real before you predicted it. This sounds like common sense. It sounds like the kind of statement nobody could reasonably disagree with. It is precisely the common sense that quantum mechanics, as it was being interpreted in 1935, was quietly violating. The example Einstein and his co-authors built around that criterion involved 2 particles. Imagine they interact briefly and fly apart. Quantum mechanics says that those particles, after the interaction, are entangled. Their properties are correlated. Not the way twins are correlated, where they happen to share certain features by common origin, but in a strict mathematical sense, in which the state of the pair cannot be written as a product of 2 individual states. The pair has properties that neither particle, taken alone, possesses. They are, in a precise and unambiguous way, no longer 2 things. They are one system described by one quantum state, regardless of how far apart they travel. Now here is the bite. If you measure the position of particle 1, you know instantly the position of particle 2. But you could just as easily have measured the momentum of particle 1, and then you would have instantly known the momentum of particle 2. Special relativity, the other great pillar of 20th century physics, says that no signal can travel faster than light. The two particles, by the time you measure them, are far enough apart that no signal can have crossed between them in time, so the measurement of particle 1 cannot, by any ordinary physical means, have caused the change in particle 2. By Einstein's reality criterion, both the position and the momentum of particle 2 must have been real before the measurement. But the uncertainty principle says that a single particle cannot possess both a definite position and a definite momentum simultaneously. So quantum mechanics, Einstein concluded, must be incomplete. There must be deeper variables hidden from us that determine the outcomes in advance. Before the EPR paper was even properly distributed, Podolsky had leaked the result to the New York Times, which ran the headline, "Einstein Attacks Quantum Theory." Einstein wrote to Schrödinger that Podolsky had buried the essential point. The essential point was about locality. Either the distant particle had its state all along, and quantum mechanics simply did not describe it, or you were forced to accept that measuring one particle could instantaneously change the physical state of a distant particle through some kind of influence that did not respect the speed of light. In a private letter to Max Born in March of 1947, Einstein gave that second option its famous name. He called it Spukhaft Fernwirkung, spooky action at a distance. The phrase was not a casual expression of wonder, it was an expression of horror. Einstein is often portrayed as a man clinging to a classical worldview out of stubbornness. That is not what was happening. Einstein understood quantum mechanics deeply. He was one of its founding architects. His 1905 paper on the photoelectric effect, the one that actually won him the Nobel Prize, introduced the very idea of quanta. He did not object to the mathematics. He objected to a specific claim that Bohr and his followers were making about what the mathematics meant. The claim was that the mathematics was the complete picture, that when quantum mechanics said a particle did not have a definite position until you measured it, that was not a statement about our knowledge. That was a statement about reality itself. The particle genuinely did not have a position. Einstein thought this was insane. He was not making a philosophical complaint. He was making a physical one. He was asking, if quantum mechanics demands instantaneous influence across any distance, what is the physical mechanism and how does it reconcile with relativity? The answer Bohr offered, in a same-titled response paper in Physical Review Volume 48, page 696, was elaborate and dense and famously elliptical. What most scholars agree on is that Bohr argued you cannot talk about the properties of a particle independent of the measurement context. The arrangements required to measure position and momentum are physically incompatible. You have to pick one. The physics community declared Bohr the winner. This was not because Bohr's argument was clearer. By any honest reading, his response is harder to understand than the EPR paper it was answering. It was because quantum mechanics worked. It made predictions of extraordinary precision. It explained atomic spectra, the structure of the periodic table, the behavior of solids and liquids and gases at the smallest scales. Why argue about interpretations when the math kept producing the right numbers? A culture developed in physics departments worldwide that would persist for the next 3 decades. The attitude was eventually captured by a phrase coined by N. David Mermin of Cornell in a column for Physics Today in 1989. Shut up and calculate. The phrase is widely misattributed to Richard Feynman, and Mermin later took pains in a follow-up column to clarify that Feynman never said it. But the phrase captured something real. If you questioned the foundations of quantum mechanics, you were not doing physics, you were doing philosophy, and philosophy did not get you a tenure position. There is a moment recorded by Abraham Pais, Einstein's colleague at Princeton, that I think about a lot. The two of them were walking together one evening. Einstein stopped, turned to Pais and asked, "Do you really believe the moon exists only when you look at it?" The question was not rhetorical. He was actually asking. He was trying to understand whether the Copenhagen interpretation, applied with full seriousness, required him to accept that macroscopic objects had no definite reality unless someone was watching them. He spent the last 20 years of his life looking for the deeper theory that would dissolve the spook. He believed the hidden variables existed. He believed the universe was locally realistic, and that quantum mechanics was a statistical approximation of a deeper deterministic structure. He died in 1955 in Princeton without finding the deeper theory. This part of the story, the Princeton War and the Moonlight Question, is where almost every popular account ends. The textbook tradition treats Einstein as the loser of a famous argument, the man whose intuitions were honourable but obsolete. The truth is more complicated. What nobody knew in 1935, what nobody would know for the next 29 years, was that the EPR argument contained a buried assumption nobody had identified. An assumption so deeply embedded in the way human beings think about the world that it would take a working-class physicist from Belfast, doing foundational work as a hobby during his vacations from his job designing particle accelerators, to drag the assumption into the light. And when he did, working alone, with no graduate students and no funding and no prestige to lose, he would prove that Einstein's escape route was not just unlikely, it was mathematically impossible. The universe, as physics had been quietly describing it for 3 centuries, could not be saved. The deeper theory Einstein spent his life hunting did not exist. It cannot exist. The mathematics will not permit it. And to understand how that proof came about, you have to follow a chain of human events that runs through some of the ugliest moments of 20th century history. Because the man whose paper would inspire the proof did not have the freedom to think about it in his own country. He had to be exiled first. Part 2. The Exile and the Pilot Wave. David Joseph Bohm was born on December 20th, 1917 in Wilkes-Barre, Pennsylvania. His father was a Hungarian Jewish immigrant who ran a furniture store. He went to Penn State for his undergraduate degree and then to Berkeley for graduate work under Robert Oppenheimer. He was, by every account, brilliant. He was also politically active in ways that would, within 15 years, destroy his career and reshape the trajectory of 20th century physics. He joined the Young Communist League at Berkeley. He attended meetings of the Committee for Peace Mobilization. During World War II, General Leslie Groves denied Bohm's security clearance for the Manhattan Project at Los Alamos. This produced one of the small absurd cruelties of the 20th century. Bohm's doctoral research on scattering calculations turned out to be useful to the bomb project and was immediately classified. He could not access his own thesis. Oppenheimer, his thesis advisor, had to personally certify that Bohm had completed the research so that he could receive his PhD, based on work he was no longer allowed to look at. After the war, Bohm got a position at Princeton. He worked closely with Einstein. They had long, slow conversations about quantum mechanics, locality, the nature of reality. Bohm wrote a textbook, published in 1951, called Quantum Theory. It is one of the clearest presentations of the Copenhagen interpretation ever written. The exercise of writing it, of laying out the Copenhagen view in its strongest possible form, convinced Bohm that something else was possible. He started to think there might be a deeper, more honest description of what quantum mechanics was actually about. And then McCarthy came for him. In 1949, the House Un-American Activities Committee called Bohm to testify about his political associations at Berkeley a decade earlier. He invoked his Fifth Amendment rights. In 1950, he was arrested for contempt of Congress. He was acquitted in May of 1951, but Princeton had already suspended him in December of 1950. The university president, Harold Dodds, refused to renew his contract, and here is the part that you should sit with. Oppenheimer, Bohm's own doctoral advisor, the man who had certified his PhD and helped him get the Princeton position, opposed his appointment at the Institute for Advanced Study and advised his former student to leave the country. The man who mentored him, who signed off on his degree, told him to flee. Bohm left for the University of São Paulo in Brazil in October of 1951. The US consulate confiscated his passport. He was, for all practical purposes, a political exile, trapped in a country where he had no roots, no community, no language he spoke fluently. He later said something I find unbearable. He said the exile liberated him. He was able to think more easily and more freely without having to speak the language of other people. There is a particular kind of irony in this, because the chain of events that leads from Bell's theorem to the most profound experimental result in modern physics passes directly through McCarthyism. If the United States government had not persecuted David Bohm for his politics, he might have stayed at Princeton, surrounded by colleagues who would have steered him away from the foundational questions the profession had decided were not real physics. His exile, his isolation, that is what gave him the room to think the unthinkable. His 1952 papers, written in involuntary exile, are the direct spark that ignites Bell's theorem 12 years later. The most important result in the foundations of physics may owe its existence to one of the ugliest episodes in American political history. We do not usually tell the history of science this way. The actual story is messier than the textbooks admit. Sometimes the breakthroughs come from people who have been pushed to the margins by their own profession or their own government, and the only thing that lets them see what nobody else sees is the fact that they have nothing left to lose. In 1952, from São Paulo, Bohm published 2 papers in Physical Review, volume 85, pages 166 and 180. The theory he laid out was a revival and extension of an idea that Louis de Broglie had proposed at the 5th Solvay Conference in 1927. De Broglie had called it the pilot wave. Wolfgang Pauli had attacked it. De Broglie had abandoned it. Bohm, 25 years later, an ocean away from Princeton, brought it back to life. The mechanics are elegant. Particles have definite positions at all times. That is the realism part. They are guided by a pilot wave, which is mathematically identical to the quantum wave function, but treated as a real physical field rather than a probability tool. The particle surfs the wave. The wave determines the particle's velocity through what is called the guidance equation. The theory is fully deterministic. If you know the initial positions of all particles in the wave function, you can in principle predict everything that will happen with certainty. There is no fundamental randomness. The apparent randomness of quantum mechanics arises because you do not, and cannot, know the exact initial positions of all the particles. The probability distribution in Bohm's theory matches the Born rule of standard quantum mechanics, the rule that gives the probability of measurement outcomes, not as a postulate added by hand, but as a consequence of the dynamics. The theory reproduces every prediction of standard quantum mechanics exactly. Every double-slit pattern, every EPR correlation, every tunneling event, every stable atom, every Bell inequality violation. Empirically, it is indistinguishable from the standard formulation. Anything the standard theory predicts, Bohm's theory predicts. Anything the standard theory says is impossible, Bohm's theory also forbids. The 2 theories give exactly the same answers for every experiment that has ever been performed and every experiment that ever could be performed using standard apparatus. But there is a catch, and the catch is the entire point. Bohm's theory is explicitly, unapologetically non-local. The velocity of any particle depends on the positions of every other particle in the universe, instantaneously, regardless of distance. The pilot wave connects everything to everything else. If you measure a particle in Paris, the pilot wave changes the trajectory of its entangled partner in Tokyo in 0 time. Not approximately 0, exactly 0. The wave does not live in ordinary 3-dimensional space. It lives in something called configuration space, a space with 3 n dimensions, where n is the number of particles in the universe. For a universe with roughly 10 to the 80th particles, the pilot wave lives in a space with roughly 10 to the 80th dimensions. The apparent separateness of the world you see around you, the feeling that this room is here and that distant star is over there and they have nothing to do with each other, is a 3-dimensional shadow cast by a higher dimensional reality that you do not directly experience. The physics establishment reacted to this with something between contempt and rage. Oppenheimer reportedly said that if we could not disprove Bohm's theory, we should agree to ignore it. Wolfgang Pauli, the same Pauli who had attacked de Broglie's pilot wave in 1927, called Bohm's revival artificial metaphysics. The theory made the same predictions as standard quantum mechanics, so it was treated as superfluous at best. At worst, it was treated as a misleading distraction, a theory that pretended to add explanatory depth but added only confusion. And there was a deeper reason to dismiss it. John von Neumann, the Hungarian mathematician, and one of the most brilliant minds of the 20th century, had supposedly proved in 1932 that hidden variable theories like Bohm's were not just unlikely, but logically impossible. Von Neumann's proof appeared in his 1932 book Mathematische Grundlagen der Quantenmechanik. For 20 years, the proof was treated as gospel. If you suggested that particles might have definite properties determined by hidden variables, the response was simple. Von Neumann proved that cannot work. Move on. Now I want to slow down here because what comes next is one of the quiet outrages of 20th century physics. Von Neumann's proof was wrong. It contained a hidden assumption that nobody had identified. The assumption was that the expectation value of the sum of two observables equals the sum of their expectation values, even for observables that cannot be measured simultaneously. This sounds technical, and it is. But the point is straightforward. The assumption is reasonable for compatible observables, things you can measure together, but it has no justification at all for incompatible observables. It is the kind of mathematical convenience that von Neumann elevated to a physical principle, and it is precisely the assumption that hidden variable theories specifically violate. A German mathematician named Grete Hermann identified this flaw in 1935. She was a student of Emmy Noether at Göttingen. She had studied the foundations of quantum mechanics with the precision of a mathematician trained in the deepest tradition of German mathematical analysis. She wrote a paper in Abhandlungen der Friesischen Schule, Volume 6, pages 75 through 152, in which she identified the hidden assumption, demonstrated that it amounted to assuming the conclusion, and showed that von Neumann's proof did not actually establish what it claimed to establish. Her paper was completely ignored. Not refuted, not engaged with, ignored. The reason is depressingly straightforward. She was a woman, in 1930s Germany, publishing in a journal that physicists did not read. She was also a member of the anti-Nazi resistance, which made her professional position even more precarious. Bell, decades later, after independently rediscovering the flaw in von Neumann's proof, described it in language that I think tells you everything about how he viewed the situation. He said it was not merely false, it was silly. You may quote me on that. Bohm, in São Paulo, did not know about Hermann's paper. He did not have to. The existence of his pilot wave theory was itself a counterexample to von Neumann's proof. If hidden variable theories were logically impossible, Bohm should not have been able to write one down. He had. The theory was on the page. It made the same predictions as quantum mechanics. It worked. The fact that the establishment continued to insist that hidden variables were impossible, even after a working hidden variable theory had been published in Physical Review, tells you something about the sociology of the field. The profession had decided what the answer to the foundational question was going to be. It was not going to be Einstein's deeper deterministic theory. It was going to be the Copenhagen interpretation, and it was going to defend that decision by citing a proof whose flaws had already been identified in 1935 by a woman the profession would not read. Bohm moved from São Paulo to Israel in 1955, and then to Bristol, and then to Birkbeck College at the University of London in 1961, where he stayed until retirement. Along the way, working with the Israeli physicist Yakir Aharonov, he discovered the Aharonov-Bohm effect, published in Physical Review Volume 115, page 485. The effect demonstrated that electromagnetic potentials, which most physicists had treated as mathematical fictions, have real physical consequences even in regions where the fields themselves are zero. Once again, Bohm was seeing something deeper in the formalism than the establishment wanted to acknowledge. He did not recover his United States citizenship until 1986, and only after a lawsuit. He died of a heart attack on October 27, 1992, in a London taxi. He was 75. He never received the Nobel Prize. The pilot wave interpretation, which Bell would describe as the most honest version of quantum mechanics ever offered, is still taught in most physics departments as an oddity rather than a foundational framework. This means that when the chain of human reasoning that leads to the demolition of local realism begins, it begins in a country to which David Bohm was not allowed to return, in a room he would have not chosen if anyone had given him a choice. The world Einstein had asked physics to defend was being defended against the institution that had refused to defend its defender by a man whose only resource was time alone with a question nobody else wanted to ask. Part 3. The Belfast Boy Who Read Bohm. John Stuart Bell was born on July 28, 1928, in Belfast, Northern Ireland. His father was a horse trader. His mother, Annie, was a dressmaker. He had an older sister, Ruby, and 2 younger brothers, David and Robert. None of his siblings continued in school past the age of 14. The family could not afford it. Only John continued, and the path was hard. He could not afford the grammar school that produced most academic physicists, so he attended Belfast Technical High School, which was not the standard pipeline to a career in theoretical physics. His mother, who could not afford to buy him the academic gown he was supposed to wear at lectures, sewed one from wartime blackout curtains. At the age of 11, John told his family he wanted to be a scientist. His parents and siblings called him the Prof. He graduated at 16 and took a job as a laboratory assistant at Queen's University Belfast because the family needed the income. This was supposed to be the end of his academic career. 2 physics professors, Carl Emilius and Robert Sloane, noticed something about the quiet teenager who was cleaning their equipment. They let him sit in on lectures, they lent him books, they encouraged him to apply for the formal degree programme. Bell earned 2 first-class honours degrees from Queen's, one in experimental physics in 1948, the second in mathematical physics in 1949. From a working-class household in Belfast, at a time when access to higher physics was almost entirely the domain of the English upper middle class, to 2 firsts at Queen's by the age of 21. That trajectory alone would have been a remarkable life. It was barely the beginning. He went to work at the United Kingdom Atomic Energy Research Establishment at Harwell. He married a fellow physicist named Mary Ross. In 1960, the 2 of them moved to CERN in Geneva, where Bell spent the rest of his career. His day job was particle accelerator design. His most cited mainstream work, the Bell-Jacques-Adler anomaly, published in 1969, solved a problem about how neutral pions decay. It is part of the standard model curriculum at every graduate physics program. By any conventional measure, Bell was a respected, established physicist in a serious field. Quantum foundations was his hobby. He pursued it, as he later put it, in evenings and on holidays. He did not discuss it openly with his CERN colleagues. He kept it separate, almost hidden, because the culture of his profession had decided that questioning the meaning of quantum mechanics was the kind of thing senile old men did. The phrase "shut up and calculate" was already in the air. The Mermin column would not appear until 1989, but the attitude was older than the phrase. Bell once said the founding fathers of quantum mechanics were right to feel uneasy. He said the problem they could not solve had not been solved by their successors. He said this in interviews. He did not say it at coffee with his accelerator design colleagues. There is a tension in Bell's life that I find revealing. By day, he was using quantum field theory to design accelerator components, trusting the math completely, relying on it to predict what would happen when particles collided at enormous energies. By night and on weekends, he was asking what that math actually meant, whether the objects it described were real, whether the predictions it made told you anything about what existed when you were not measuring. Most of his colleagues saw no contradiction. The math works. Why ask more? Bell could not accept that answer. And the thing that set him on the path to his theorem was something he read in 1952. Something the physics establishment had decided should not exist. He read Bohm's pilot wave papers in Physical Review. He had been told, like every graduate student of his generation, that hidden variable theories were logically impossible because of von Neumann's 1932 proof. He read Bohm's 1952 construction, which was a hidden variable theory that worked. He has described the moment in later interviews. He said he saw the impossible done. If the impossible was possible, if Bohm could write down a working hidden variable theory despite von Neumann's supposed impossibility proof, then something must be wrong with the proof. Bell went back to the original. He worked through it line by line. He identified the assumption von Neumann had buried, the sum of expectation values assumption, and he saw what Greta Herrmann had seen in 1935, without knowing that she had seen it. The assumption was unjustified. The proof was, as he later put it, not merely false but silly. In 1963 and 1964, Bell took a sabbatical year. He went first to Stanford, then to the University of Wisconsin, then to Brandeis. He used the time to think about the foundational question that had been gnawing at him since he read Bohm. He produced 2 papers. The first, written first but published later because of editorial delays, appeared in Reviews of Modern Physics in 1966. That paper was the formal demolition of von Neumann's proof. Bell laid out exactly what was wrong with the hidden assumption, and he showed why the standard interpretation of the proof was unjustified. He also surveyed the other impossibility proofs that had accumulated in the literature since 1932, by Andrew Gleason in 1957, by Simon Kochen and Ernst Specker in 1967, and showed how they all required assumptions about how measurements combine that hidden variable theories explicitly did not have to satisfy. That paper cleared the ground. It said, in effect, the impossibility proofs do not actually prove what they claim to prove. Hidden variable theories are not logically impossible. The door is open. The second paper asked the deeper question. If hidden variable theories are possible, can you build a local one? Bohm's theory was non-local. It connected every particle to every other particle through a wave that lived in configuration space. Was the non-locality a defect of Bohm's particular construction, or was it forced by something in nature? Could someone build a local hidden variable theory that reproduced the predictions of quantum mechanics? Could you keep Einstein's locality and still have particles with definite properties? What Bell found is the most consequential result in the foundations of physics, and I want to walk through it carefully, because the logic is accessible to anyone willing to follow a few steps of reasoning. It does not require advanced mathematics. It requires patience and a willingness to think about correlations. Imagine 2 particles that are created together in a particular quantum state called the singlet state, and sent in opposite directions to 2 detectors that are far apart. Each detector can be set to one of several different orientations. Think of each detector as a polarizer that you can rotate. When a particle hits a detector, the detector gives one of 2 possible results, +1 or -1. The orientation of the detector determines the angle at which the particle is being measured. The result, plus or minus, depends on that angle and on the particle's properties. Now, if the particles carry their own pre-existing properties, if each particle is, in effect, walking around with a hidden instruction sheet that tells it what to do at every possible detector angle, and if the detectors are far enough apart that no signal travelling at the speed of light can carry information between them in time, then the correlations between the results at the 2 detectors are constrained. They cannot be just any correlations. They have to obey a specific mathematical limit. The key insight, the thing Bell saw that nobody else had seen in the 30 years since EPR, is that the constraint becomes visible only when you combine measurements at multiple detector angles. If you only look at a single pair of angles, the correlations from a hidden variable theory and the correlations from quantum mechanics look exactly the same. The 2 theories agree, but if you measure at multiple pairs of angles and combine the correlations, the assumption of locality forces the hidden variable theory to compromise. The particles cannot be correlated at every angle simultaneously because the instruction sheet has to commit to specific answers in advance. Each instruction sheet has finite capacity. Quantum mechanics is not constrained this way. Its correlations are stronger. Let me make this concrete with an analogy. Suppose you and a friend are in separate rooms. Before you were separated, you both received envelopes that were prepared in advance by someone else. Each envelope contains a card that says either plus or minus. The person who prepared the envelopes could have chosen any combination of pluses and minuses. The contents of the envelopes are fixed in advance, and your opening your envelope cannot change what is in your friend's envelope. That is local realism, expressed in the simplest possible terms. Now suppose you and your friend each have several envelopes, one for each of several possible questions. The questions correspond to detector orientations. The contents correspond to measurement outcomes. The correlations between your answers, across all possible questions, are constrained by the fact that the envelopes were filled in advance. There is a ceiling on how correlated your answers can be. That ceiling is 2. Specifically, in the standard form of Bell's inequality known as the CHSH inequality, named for John Clauser, Michael Horn, Abner Shimony, and Richard Holt, who derived it in 1969. The correlation parameter S can be at most 2 for any local realistic theory. 2 is the absolute maximum that a universe of envelopes, a universe where every measurement outcome is fixed in advance by hidden variables and where local interactions are the only physical influences, can produce. Quantum mechanics does not respect the ceiling. Quantum mechanics says the particles do not have envelopes. The answers are not fixed in advance, and because they are not fixed, the correlations can be stronger than any envelope system could produce. The quantum prediction for the singlet state at optimal detector angles of 0, 22.5, 45, and 67.5 degrees is S equals 2 times the square root of 2, or approximately 2.828. That is not slightly above the local realist ceiling, it is 40% above it. The universe, in other words, is more correlated than classical envelopes could ever be. Bell published this result on November 4, 1964. The paper appeared in a journal called Physics, Physique, Physica. It was a trilingual journal, published in English, French and Russian. It accepted no page charges. In fact, it paid Bell a small fee for the paper. The journal folded after a few issues. Bell's paper accumulated fewer than a dozen citations in its first 6 years. Let that land for a moment. The most important result in the foundations of physics appeared in an obscure journal that no longer exists, written by a man whose day job was designing accelerator magnets, hidden as a hobby because the culture of his own profession had decided that asking what quantum mechanics meant was not real physics. I think about this part of the story a lot. Not the physics, the sociology. The most profound theorem in the history of science was published in a dead journal as a side project. The man who wrote it had to hide his interest in foundational questions from his CERN colleagues, and the proof was sitting in the literature, waiting for someone to translate it into an experimental procedure that would let nature herself say which side of Bell's inequality the universe was on. That experimental procedure would take 8 more years to construct in a basement at Berkeley by a graduate student and his advisor working on a shoestring. And the advisor would be told by the most famous physicist alive at the time to stop wasting time on the question and go do real physics. We are getting to that. But first I want you to sit with the image of John Bell in a CERN office in 1964, mailing his paper to a journal that would not exist a few years later, knowing that his colleagues would not be interested, knowing that the profession had decided the question was not worth asking, and asking it anyway, on a hobby basis, in his spare time, because the question would not let him go. Part 4. The sub-basement at Berkeley and the office at Caltech. John Francis Clauser was born on December 1, 1942 in Pasadena, California. His father, Francis Clauser, was a professor of aeronautical engineering at the California Institute of Technology. His uncle, Edwin Macmillan, had won the Nobel Prize in Chemistry in 1951 for the discovery of transuranium elements. Physics ran in the family, but not this kind of physics. The Clauser household was a household of aerospace engineering and reactor chemistry. It was not a household where graduate students sat around the dinner table, arguing about the nature of reality. John Clauser went to Caltech for his undergraduate degree, and then to Columbia for graduate school in the late 1960s. While at Columbia, he stumbled across Bell's 1964 paper. He has described the moment in interviews as transformative. Here was a mathematical proof, in a journal almost nobody read, that you could actually test in the laboratory whether the universe was locally real. The proof gave a specific number. The correlation parameter S could be at most 2 for any local realistic theory, and quantum mechanics predicted that S could reach 2 times the square root of 2. The difference between 2 and 2.828 was something you could in principle measure with photons and polarizers. Nobody was doing it. Nobody at Columbia, nobody at Princeton, nobody at any of the major American physics departments was bothering to test the result. Clauser found this baffling. Here was the most important experimental question in the foundations of physics, with a specific experimental procedure that would settle it, and the profession had decided the question was not worth answering. His professors told him not to do it. The subject was considered professionally disreputable. Testing the foundations of quantum mechanics was not real physics. It was philosophy. Philosophy did not lead to grants. It did not lead to publications in respected journals. It did not lead to faculty positions. Clauser pushed forward anyway. He co-authored the CHSSH inequality paper in 1969, while still a graduate student. The paper appeared in Physical Review Letters, Volume 23, page 880. The CHSH inequality is the experimentally testable form of Bell's theorem, the version that physicists could actually take into the lab. Almost every Bell test that has ever been performed uses the CHSH inequality, or a close cousin of it. I want to pause and tell you something about Clauser that I find genuinely moving. He actually expected the experiment to confirm local realism and disprove quantum mechanics. He thought Einstein was right. He wanted the hidden variables to win. He designed and built the apparatus hoping to prove that Bell's inequality was respected by nature, that quantum mechanics, despite its many successes, was an incomplete statistical approximation of a deeper, locally real theory. The fact that he ran the experiment despite his own expectations, and then accepted the result when it turned out to contradict his beliefs, tells you everything about what kind of scientist he was. He let the universe answer, and he respected the answer even when it was not the one he wanted. That takes a specific kind of courage, not the courage of the person who charges into battle knowing they are right, the courage of the person who builds the machine that might destroy their own beliefs and turns it on anyway. In 1971, Clauser moved to the University of California at Berkeley as a postdoctoral researcher at Lawrence Berkeley Laboratory. He set up the first serious experimental test of Bell's inequality in a sub-basement of Burge Hall. He had essentially no funding. He scrounged equipment from other labs. He built the apparatus from parts that, in some cases, he literally pulled from the trash. He recruited a graduate student named Stuart Friedman to work with him. The photon source was a calcium atomic cascade. Excite a calcium atom with ultraviolet light from an arc lamp, and the atom falls back to its ground state by a two-step process, emitting 2 photons entangled in polarization in roughly opposite directions. Put a polarizer in each beam, count the coincidences, measure the correlation. The polarizers Clauser and Friedman used were single-channel pile-of-plates devices. You only counted photons in the transmitted channel and discarded the reflected ones. This is the detection efficiency problem in its earliest form. To get a result, you have to assume the pairs you see are representative of all the pairs. They collected data for 200 hours. 200 hours of watching counters tick in the sub-basement, in the dim light. Some nights they would log fewer than 1,000 coincidences across the entire shift. Clauser had set the experiment up expecting Einstein to be right. Every hour of data collection was a slow-motion confrontation with the possibility that reality was not what he thought it was. The result, when they finally had enough data, was a parameter that they reported in a form related to Bell's original inequality. The version published in Physical Review Letters, Volume 28, page 938, in 1972 was 0.300 plus or minus 0.008 against a local realist bound of 0.250. The violation was 6.3 standard deviations. That was the first experimental proof that local hidden variable theories are wrong. The result was published. It was correct. It was confirmed by independent experiments within a few years. It should have detonated. It did not. What happened next is the part of the story that I find genuinely damning. Clauser took his result to Caltech. He wanted to show it to Richard Feynman. Feynman was, in 1972, arguably the most famous physicist alive. He was the author of the Feynman Lectures, the architect of quantum electrodynamics, the man who had explained quantum mechanics to 2 generations of physicists with a clarity that nobody had matched before or since. Clauser thought Feynman would be interested. He thought Feynman, of all people, would want to know that a fundamental question about quantum mechanics had been answered by experiment. He was wrong. Clauser has described the meeting in multiple interviews. By Clauser's own account, Feynman became highly offended by his impertinent effort. Feynman insisted that testing quantum mechanics was tantamount to professing a disbelief in it. He said that quantum mechanics was obviously correct and needed no further testing, and he more or less threw Clauser out of his office. Clauser left with the result in his briefcase, and no idea what to do with the fact that the most famous physicist alive had just told him he was wasting his time. Other physicists Clauser approached gave similar responses. "Nice experiment," they said. "Now stop wasting time and money and go do some real physics." Clauser later said that this kind of reaction was so universal that he eventually stopped trying to discuss the result with senior physicists. He moved into other areas of physics for much of his career. He never held a tenure-track professorship. The experiment that first proved the universe is not locally real effectively ended his conventional academic career. He survived as a research scientist, picking up grants where he could find them, doing serious work in adjacent fields. He waited until 2022 for his Nobel Prize. He was 80 years old when he received the phone call. There was a competing experiment at Harvard during this same period, run by Richard Holt and Francis Pipkin. The Harvard team used a mercury isotope and got a result that briefly appeared to support local realism, disagreeing with quantum mechanics by nearly 4 sigma. For a few confusing years in the mid-1970s, there was genuine doubt. Clauser repeated the experiment in 1976 with a different mercury isotope and discovered the anomaly was caused by stressed Pyrex glass introducing erroneous polarization readings. An independent experiment by Edward Fry and Randall Thompson at Texas A&M confirmed quantum mechanics in 80 minutes. The result was a measurement artifact, not a reflection of physics. But Clauser's experiment, as decisive as it was for the existing loopholes of the time, had a structural weakness. The polarizer settings were fixed in advance, before the photons were emitted. In principle, some unknown subliminal signal could have communicated between the detectors and the source, coordinating the results. Bell himself had specifically called for experiments in which the polarizer settings were changed during the flight of the particles. He had said it in interviews. He had said it in his papers. What was needed was an experimentalist willing to spend years building an apparatus that could switch detector settings faster than light could travel between them. That kind of switching is not a small engineering problem. It requires optical components that change orientation in nanoseconds. It requires acousto-optical modulators driven by ultrasonic standing waves. It requires the kind of patience and resources that only a senior research group at a serious optics laboratory can sustain. There was such a place. There was such a person. There was a 35-year-old French physicist named Alain Aspect, working at the Institut d'Optique in Orsay, just south of Paris. He had read Bell's 1964 paper. He had described the experience as love at first sight. He had spent the last 5 years building an apparatus that would do exactly what Bell had called for, that would close the locality loophole that Clauser had not been able to close, that would push the result from 6.3 sigma to 40 sigma, and that would finally answer the question Einstein had asked at Princeton in 1935, with the kind of certainty that physics had never produced for any other measurement. He had been warned by Bell himself that a majority of physicists would consider him a crackpot for doing this work. He had done it anyway. Part 5. The Basement at Orsay. Alain Aspect was born on June 15th, 1947, in Agen, a small city in southwestern France. He finished his master's thesis on holography, and then, as a young man, went to Cameroon for his civil service. He chose to teach rather than serve in the military. While he was teaching in Cameroon, he bought the textbook by Claude Cohen-Tanuji, Bernard Dieu, and Frank Laloux, and he taught himself quantum physics properly. He has said publicly, in lectures and interviews, that his university quantum mechanics course in France was, and I am paraphrasing here, very bad teaching. He learned the real subject from a book in Africa, on his own, by working through every problem by hand. When he returned to France in 1974, he obtained a permanent position as maître assistant at the École Normale Supérieure de Cachan. This is a critical detail. In the French academic system, this was a tenured position, obtained without a PhD. It gave him job security he would later need. He then went looking for a thesis topic. He visited laboratories. He asked researchers for interesting problems. At the Institut d'Optique in Orsay, just south of Paris, someone handed him a file that contained Bell's 1964 paper. He read it in about an hour. He has described the experience in language that I find genuinely beautiful. He said it was love at first sight. After that single hour, he knew that he wanted to devote his thesis to testing Bell's inequality. In 1975, Aspect travelled to CERN to meet Bell in person. The meeting has become legendary in the physics community. Aspect has told the story so many times that the language is precise. He has said he was very impressed to meet Bell, who looked very serious. Bell sat in silence while Aspect explained his experimental idea. The plan was to build an apparatus that could switch detector orientations while the photons were already in flight, closing the locality loophole that Clause's experiment had left open. When Aspect finished, Bell asked his first question. It was not a question about the physics. It was, "Do you have a permanent position, young man?" Aspect said yes. He explained the French system, the tenured position without a PhD. Bell replied, "Okay, very good. Let us talk science." After they had discussed the physics for a while, Aspect asked why Bell had wanted to know about his job security before discussing the experiment. Bell told him, plainly, that a majority of physicists would consider him a crackpot for doing this work. A majority. Not a fringe minority of old guard traditionalists. A majority of working physicists in 1975 would have considered Aspect professionally deranged for experimentally testing the foundations of quantum mechanics. Bell wanted to make sure Aspect could afford the social cost of the work before he encouraged him to do it. There is one more detail from that meeting that I love. When Aspect proudly asked if he could keep his experimental scheme confidential, worrying that a competitor might steal the idea, Bell responded, "Young man, we are doing basic research." The implication was clear. This was not about priority or credit. This was not about the next physical review letters paper. This was about answering a question that mattered. The crackpot warning and the gentle correction about basic research, in the same conversation, in the same room at CERN, give you a sense of what Bell was like. He was kind. He was serious. He was prepared to defend the question against the profession that had decided the question did not matter. Aspect spent approximately 5 years designing and building his apparatus. His innovation was the photon source. He used a calcium-40 atomic cascade, exciting the atoms with 2 lasers simultaneously, a krypton-ion laser at 406 nanometers and a tunable dye laser at 581 nanometers. The cascade produced entangled photon pairs at wavelengths of 551.3 nanometers, green light, and 422.7 nanometers, violet light. The intermediate state in the cascade had a lifetime of about 5 nanoseconds. Two feedback loops maintained the system's stability to better than 0.5% over several hours of continuous running. The production rate was extraordinary, 40 to 50 million entangled photon pairs per second. Where Clauser had needed 200 hours to get his result, Aspect could achieve 1% statistical accuracy in 100 seconds. The first Aspect experiment was published in August of 1981 in Physical Review Letters, Volume 47, page 460, with Philippe Grangier and Gérard Roger. They used single-channel polarizers, like Clauser had. The violation of Bell's inequality was 9 standard deviations, clean, unambiguous, in excellent agreement with quantum mechanical predictions. The polarizers were separated by 6.5 meters, which was about 4 coherence lengths. That separation refuted a hypothesis put forward by Wendell Furry in 1936 that entanglement should vanish beyond the coherence length. It does not. Entanglement does not have a finite range. The second Aspect experiment came in July of 1982. This was the breakthrough. Aspect used 2-channel polarizing cubes that transmitted one polarization and reflected the orthogonal one, making the apparatus a true optical analogue of a Stern-Gerlach device. For the first time in the history of Bell tests, 4 coincidence circuits counted all 4 possible outcome combinations simultaneously: plus plus, plus minus, minus plus, minus minus. You no longer had to discard the photons that did not make it through your polarizer. You counted every photon in both channels on both sides. The polarizer angles were set at the optimal Bell test values, 22.5 degrees apart, where quantum mechanics predicts the maximum violation. The result was S equals 2.697, plus or minus 0.015, a violation of the CHSH bound of 2 by more than 40 standard deviations. Aspect has stated in later interviews that the value is closer to 50 sigma when systematic effects are accounted for. It was 83% of the maximum possible quantum violation, which is 2 times the square root of 2, or 2.828. The polarizers were separated by 13 meters. I want you to be in the basement with him while this is happening. Imagine the Institut d'Optique in Orsay in July of 1982. A research building south of Paris, a few floors below ground level. The corridor lights dim, the smell of cooling water for the polarizing cube assembly, the soft hum of the arc lamp at the calcium-40 source. Aspect at the bench, 35 years old, the man who came back from teaching in Cameroon and read Bell's paper in an hour. Grangier on the coincidence counter side, watching the numbers accumulate. Roger checking the optical alignment, making sure the beam paths are clean. The detector clicks are faint. The coincidence rates are higher than they were in the Berkeley basement a decade earlier, but they are still slow. The number on the readout, the running estimate of the CHSH parameter, is climbing. It passes 2. It passes 2.5. It settles near 2.697. 8,000 seconds of data. Aspect's hands on the data sheet, the careful tabulation of the standard deviations, the gradual recognition that the universe has just answered the deepest question physics has ever asked. And the answer is the one Einstein had spent his last 20 years trying to escape. The number is 2.697. Remember it. It will come back at the end of this story with a different weight. But the second experiment, decisive as it was for the existing loopholes of the time, still left the locality loophole open. The polarizer settings were fixed in advance. Bell had specifically said that the experiment needed to switch the settings during the flight of the photons. That was the third experiment, published in December of 1982 in Physical Review Letters, Volume 49, page 1804, with Jean Dalibard and Gérard Roger. This is the one Bell had been waiting for. Aspect replaced the fixed polarizers with acousto-optical switches, an ultrasonic standing wave in a tank of water, driven at approximately 25 MHz, deflected the photons between 2 differently oriented polarizers. The effective switching occurred at about 50 MHz, with complete orientation changes every 6.7 to 13.3 nanoseconds. The two switches were driven at slightly different frequencies by independent radio frequency generators, which made the switching pattern quasi-random. The two switches were not synchronized. They were not predictable. Here are the numbers that matter, and I want you to follow them carefully because the entire argument turns on them. The distance between the two switches was 13 meters. Light takes approximately 40 to 43 nanoseconds to travel that distance. The switching intervals were 6.7 to 13.3 nanoseconds. The photon emission delay from the calcium cascade was about 5 nanoseconds. Both the switching interval and the emission delay were small compared to the time it takes light to cross from one detector to the other. A detection event on one side and the corresponding setting change on the other side were, in the language of special relativity, space-like separated. No signal travelling at the speed of light or slower could have carried information between them. For the first time in the history of physics, the polarizer settings were chosen while the photons were already in flight, with enough timing margin that no light-speed signal could have coordinated the choices with the results. I need to explain what space-like separated means, because the entire argument depends on it. In special relativity, two events are called space-like separated if no signal travelling at or below the speed of light can connect them. They're too far apart in space and too close together in time. Nothing, no signal, no wave, no field, no influence of any kind that respects the speed of light, can pass between them. If the detection event at detector A and the setting choice at detector B are space-like separated, then there is no physical mechanism consistent with special relativity by which the setting at B can have influenced the outcome at A, or vice versa. This is not a practical limitation about current technology. It is a fundamental constraint of space-time geometry. Nothing can travel between space-like separated events, and yet the correlations were still there. The acousto-optical switches change the polarizer orientations every few nanoseconds. The photons hit the detectors. The CHSH parameter accumulated. The data collection ran for 8,000 seconds for the Bell test itself, and another 16,000 seconds for auxiliary measurements. The beam apertures had to be cut by a factor of 3 to fit the switch geometry, which dropped the true coincidence rates to just a few per second, with accidental coincidences at about 1 per second. The result was quantum mechanics predicted 0.112 for the relevant correlation. Aspect measured 0.101, plus or minus 0.020. Agreement within error bars. Violation by 5 standard deviations. The locality loophole, for all practical purposes, was closed. There was no way, consistent with relativity, that a signal could have coordinated the two detectors. The universe had been asked, under the strictest conditions ever imposed, whether it was locally real. It had answered no. Aspect had produced the most profound experimental result since the discovery of quantum mechanics itself. The framework that had guided physics since Newton, the assumption that objects have definite properties and can only be influenced by their immediate surroundings, was, by the most stringent test that had ever been performed, false. This should have been the moment. This should have been front-page news. It should have triggered an intellectual earthquake. It should have stopped the entire physics community in its tracks and forced a public conversation about what kind of universe the data actually described. And here is what happened instead. Almost nothing. The number 2.697 landed in Physical Review letters and produced approximately 0 ripples. The community shrugged. We were about to walk into the silence that followed, and the silence is, in many ways, the deepest part of this whole story. Because the silence tells you something not about quantum mechanics, but about what a profession does when its experimental data demolishes its picture of reality, and the people in the profession would rather not look. Part 6. The Silence. The result was met with indifference. That is the simplest way to put it, and it is also the truest. Aspect himself described the reception years later in his Nobel podcast in 2022. He said, "Mostly nobody cared, for several good reasons. The most important reason, he said, was that it was perceived to be only about interpretation. If you were a young physicist, active in your field, using quantum mechanics every day, the math worked. Why would you care about an epistemological debate between two old glories from the early 20th century? Einstein had been dead for 27 years. Bohr had been dead for 20. The argument that started at the Fifth Solvay Conference in 1927 was something that belonged to the history of physics, not to its present. The Nobel Committee Scientific Background document for the 2022 prize confirms this assessment with unusual frankness. The document is on the Nobel Prize website. You can read it for yourself. It says, in language remarkably direct for an institutional Nobel document, that some people said this was really weird, but they dismissed that thought because the status quo already held that quantum mechanics is strange. The inclination of the research community at the time was to just carry on using quantum mechanics and not worry about what it meant. That is the Nobel Committee in 2022 telling you in its own words why nothing happened in 1982. The profession decided to keep calculating. It was not just passive indifference, it was actively enforced. There is a famous story about a conference on quantum foundations at Eris, in Sicily, in 1985. The organiser wanted to invite John Bell to give the opening lecture. Several senior physicists objected, not because they thought Bell's mathematics was wrong. The mathematics was not controversial. They objected because they thought the topic was inappropriate for a serious physics conference. Foundations was philosophy. Philosophy was not physics. So the most mathematically precise result in the foundations of physics was being dismissed by senior figures in the field as the wrong kind of question for a physics meeting. That tells you something about the pathology of the culture. John Clauser described that culture in even more devastating language. He said a severe stigma began to develop within the physics community against anyone who, in his words, sacrilegiously was critical of quantum theory's fundamentals. Any physicist who openly criticised or even seriously questioned these foundations was immediately branded as a quack. The interesting thing, Clauser said, is that there remained alive a minority of the theory's founders, Einstein, Schrödinger, de Broglie, who had been critical of the standard interpretation throughout their lives. These men were obviously not quacks. They had Nobel Prizes. Instead, the gossip among physicists in the 1970s and 80s branded them senile. I want you to sit with that for a moment. The profession's defense mechanism against uncomfortable questions was to declare that the people asking them, including three of the greatest physicists who ever lived, were experiencing cognitive decline. The dismissal was not intellectual, it was personal, it worked for decades. It allowed the profession to continue using a theory whose foundations it had decided not to examine, by attributing the desire to examine those foundations to senility on the part of the founders. The most important experimental result in the foundations of physics was published, verified, and quietly filed away. The establishment acknowledged the data and turned back to their accelerators, their condensed matter systems, their string theories. The results sat in the literature like a loaded gun nobody wanted to pick up. And here is where the human cost of the story becomes most visible, because the people who had asked the question, the people whose work had produced the answer, were paid for their work in a particular way, and the payment was professional silence. Hugh Everett III had proposed the many worlds interpretation as his Princeton PhD thesis in 1957 under John Archibald Wheeler. The interpretation said there is no collapse of the wave function. The Schrödinger equation applies universally, always. When a measurement happens, all the outcomes occur in different branches of the universal wave function. We'll get into many worlds in detail later. For now, the relevant biographical fact is what happened to Everett. Wheeler, his own advisor, made him cut the thesis from 137 pages to a thin 27-page version that removed most of the philosophical implications. Bohr's associate, Leon Rosenfeld, was actively hostile. When Everett visited Copenhagen in 1959, the reception was cold. Rosenfeld later described many worlds as theology, which in physics is not a compliment. Everett never got an academic physics position. not because he could not do the work. He was by every measure brilliant, but the culture of the profession had decided that thinking seriously about what quantum mechanics means was not real physics. So Everett went into military operations research at the Pentagon's Weapons Systems Evaluation Group and later the Institute for Defense Analysis. He became wealthy. He also became an alcoholic and a heavy smoker. He died of a heart attack on July 19, 1982, at the age of 51. His daughter Elizabeth, who struggled with mental illness, took her own life on June 24, 1996. In her note, she expressed the hope of ending up in the same parallel universe as her father. His son, Mark Oliver Everett, who would later become the lead singer of the band Eels, said in a BBC documentary in 2007 that he did not know his father had been a famous physicist until the documentary was made. He had found his father's body as a teenager. He had not understood why his father had spent so much of his life drinking instead of doing physics. The answer, of course, is that the physics community told him his most important idea was not worth pursuing. David Bohm died on October 27, 1992 in a London taxi. Heart attack, 75 years old. He had recovered his United States citizenship only 6 years earlier, in 1986, and only after a lawsuit. He had spent 40 years watching the physics establishment ignore the work he had done in São Paulo. The pilot wave theory, which Bell would call the only honest interpretation of quantum mechanics, was still being taught in most departments as an oddity, a footnote. He died in a city that was not his home, in a country that had revoked his right to return to his home for 35 years, having spent his last decade trying to explain in books and lectures what most physicists were not interested in hearing. He never received the Nobel Prize. He never received the recognition that his theory deserved. He had been right too early. The cost of being right too early was to be ignored by the profession until you died. John Stuart Bell died of a cerebral hemorrhage on October 1, 1990 in Geneva. He was 62 years old. According to multiple credible sources, including the MacTutor History of Mathematics archive at St Andrews and Physics World magazine, Bell had been nominated for the Nobel Prize that year. The Nobel nomination records are sealed for 50 years. The 1990 records will not be public until 2040. The claim that Bell was nominated cannot be formally verified yet. But the pattern of major awards Bell received in his final years tells you what the community had finally figured out. The Hughes Medal from the Royal Society, the Dirac Medal, the Heinemann Prize, honorary degrees from Queen's University Belfast and Trinity College Dublin. The establishment had, after 40 years of silence, started to catch up to the magnitude of what he had done. He died weeks before what many in the physics community believed would have been his Nobel. His final published paper, Against Measurement, had appeared in Physics World in August of 1990, weeks before his death. It is a characteristically aggressive critique of the use of the word measurement as a fundamental term in quantum mechanics. He argued, in language that I find almost painful in its precision, that if a fundamental physical theory requires the word measurement to function, then the theory does not understand what it is describing. He was challenging the profession's most sacred cow with his last published words. That was Bell. He could not stop pulling at threads, even when nobody wanted to see what unravelled. His wife Mary, also a physicist at CERN, survived him. He was an atheist. He was a vegetarian. In his version of Schrödinger's cat, he replaced the alive and dead states with hungry and not hungry, because he did not want to think about killing cats, even hypothetical ones. Roman Jacquieu, who worked with him on the chiral anomaly, described his overwhelming intellectual precision and honesty. He retained his Belfast accent his entire life. He worked at CERN until the morning of the day he died. He spent the afternoon at home, with the foundational problem that had been his hobby for 40 years, and then he had the cerebral hemorrhage, and he died on the floor. Stuart Friedman, the graduate student who had co-performed the first Bell test with Clauser in the Berkeley sub-basement, moved on to nuclear and neutrino physics. He became a respected figure in those fields. He died on November 10, 2012, at the age of 68. He died a decade before the 2022 Nobel that finally recognized the work he had helped make possible. Abner Shimoni, the philosopher-physicist who co-derived the CHSH inequality, who helped make Bell's abstract theorem experimentally testable, who gave the entire field its mathematical framework, died in 2015, 7 years before the prize. He never got the call. The prize was finally awarded on October 4th, 2022 to Alan Aspect, John Clauser, and Anton Zeilinger for what the citation called experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. Clauser was 80 years old. Aspect was 75. 40 years had passed since the experiment in Orsay. The man who had made the theorem possible had been in the ground for 32 of those years. At the Nobel ceremony in Stockholm, Aspect spoke first. His words were precise and chosen with care. He said that recognition should go first to the late John Stuart Bell, without whom we would not be here today. He told the story of the permanent position warning to the Nobel audience. 40 years for a Nobel after the experiment was performed. Most of the people who had paid the cost of doing the work were not alive to hear his thanks, and so the data was in. The result had been confirmed. The Nobel had been awarded. The question of what the result actually means, of what kind of universe the data describes, was the question the profession had been refusing to face for 40 years. The result is that anyone now standing in front of the four doors is standing alone. Or almost alone. We are standing in front of those four doors together right now, and I want to walk you through them, one at a time, because they are the only places the mathematics will let you stand. There is no fifth door. The mathematics will not allow it. Part 7. Door 1. Non-locality. The first door is the one Bell himself walked through. The first door is the one Bohm built in São Paulo in 1952, in the years after the United States revoked his passport. The first door is non-locality. To walk through this door, you accept that particles do have definite properties at all times. You accept that the moon exists when nobody looks at it. You accept that the chair you're sitting on has a definite shape and a definite mass and a definite location, whether or not anyone is observing it. In exchange, you accept that the universe is connected to itself instantaneously, across any distance, through influences that do not respect the speed of light, that do not respect the geometry of space-time, that do not respect any boundary or any signal limit you have ever been taught about. In Bohm's theory, the particles are real and definite. They have positions at all times. They are guided by a wave that lives, not in the three-dimensional space you experience, but in something called configuration space, a space with 3 n dimensions, where n is the number of particles in the universe. For a universe containing roughly 10 to the 80th particles, the guiding wave lives in a space with roughly 10 to the 80th dimensions. You cannot see this wave. You cannot experience this wave directly. The wave is the actual structure of physical reality, and the three-dimensional world you see is a shadow it casts. The wave determines the velocity of each particle through what is called the guidance equation. And here is the part that matters for door 1. The velocity of any particle depends on the positions of every other particle in the universe, instantaneously, regardless of distance. If you perturb a single electron in a laboratory on Earth, even by the smallest possible amount, the guiding wave changes. The wave change is felt by every other particle in the universe in 0 time. The electron in your hand and the electron at the centre of a galaxy 13 billion light-years away are connected by the same wave. Move one. The other one knows. Let me make this concrete with the aspect experiment, because this is exactly the structure the aspect data demands. 2 entangled photons fly apart from a calcium-40 cascade in Orsay. They reach detectors that are space-like separated. The detectors choose, while the photons are in flight, what angles to measure at. In Bohm's framework, both photons have definite polarizations the whole time. They are real. They are not in some hazy superposition of properties. They have actual orientations. But the guiding wave, which lives in the higher dimensional space, knows about both detectors simultaneously. When detector A's switch decides on its angle, the guiding wave updates. The wave update is felt at detector B in 0 time. The polarization of the photon at B, which had been definite all along, now reflects the change. The detection event at B carries the imprint of the choice at A, even though no light speed signal could have crossed the 13 meters between them in the available nanoseconds. I want to be precise about what instantaneously means here, because the word is easy to understate. It does not mean very fast. It does not mean approaching the speed of light. It means literally 0 delay. In Aspect's third experiment, the switching events and the detection events were separated by a space-like interval. No signal travelling at the speed of light could have carried information between them, but the correlations were still there. In the cosmic bell test of January 11, 2018, on La Palma, the detector settings were determined by photons that had been travelling through space for 12.2 billion years. The correlations were still there. Whatever connects entangled particles, it does not care about distance. It does not care about meters. It does not care about kilometers. It does not care about billions of light years. I want you to imagine for a moment standing at the cosmic event horizon. The cosmic event horizon is 16.59 billion light-years away under the standard cosmological model. It is the boundary beyond which any signal we send today, in any direction, will never reach. Imagine you are standing there, at the absolute limit of what can ever be in causal contact with Earth. You are holding a photon in your hand. The photon is entangled with a partner that sits, right now, on a laboratory bench at the Institut d'Optique in Orsay, France. Someone in Orsay decides to measure the partner. They choose an angle. They turn the polarizer. In 0 time, the wave function of the photon in your hand updates. The connection is not a signal. It is geometry. The space between you and the laboratory is not a barrier and not a bridge. It is, for the purposes of the connection, irrelevant. The pilot wave makes no distinction between the back of your own hand and the inside of a galaxy 13 billion light-years away. The separateness of distant things, the feeling that this room is here and that distant point is over there, and they have nothing to do with each other, is the surface of an ocean. Underneath, everything touches everything. The philosopher of physics Tim Maudlin has argued that this should not be called non-locality in the relativistic sense, because there is no signalling. He is partly right. The Bohmian framework respects the no-signalling theorem of quantum mechanics, which I will come back to in a moment. But Maudlin himself notes that it is certainly non-locality in the ordinary English sense. Things that are far apart are not independent. Period. The pilot wave does not respect any meaningful notion of locality you have ever experienced in your daily life. Now you might object fairly that this seems to violate special relativity. It does not, or at least it does not in any way you can exploit. The no communication theorem, proved rigorously within quantum mechanics, shows that you cannot use entanglement to send information faster than light. The argument is precise, and I want to walk through it because it is the only thing that keeps non-locality consistent with relativity. When Alice measures her half of an entangled pair, she gets a random result. +1 or -1, 50-50, completely unpredictable from her end. Bob, measuring his half, also gets a random result, 50-50. Neither Alice nor Bob can tell, from their own local statistics, that anything has happened on the other side. The non-locality only becomes visible when they bring their results together, using ordinary classical communication that travels at or below the speed of light. Only when they compare notes do they see that their random +1 and -1 outcomes are correlated in ways that classical physics could never produce. The physicist John Jarrett decomposed Bell's locality conditions into 2 independent conditions in 1984. He called them parameter independence and outcome independence. Parameter independence says that Alice's outcome probability does not depend on Bob's choice of measurement setting. Outcome independence says that, given the hidden state in both settings, Alice's specific outcome does not depend on Bob's specific result. Standard quantum mechanics violates outcome independence while preserving parameter independence. Bohm's theory does it the other way around. But in both cases, the violation cannot be used for signaling, because you would need to know the hidden state to exploit it, and the hidden state is precisely what you do not have access to. What this means practically is that the non-locality is hidden in the correlations. It is invisible to either party individually. It only becomes visible when you bring the results together. It is as if the universe is whispering a secret to itself, and you can only hear it if you compare notes from both sides. Neither side alone hears anything unusual. Abner Shimoni, in a phrase I find deeply moving, called this passion at a distance rather than action at a distance. The cost of door 1 is steep. To accept Bohm, you accept that the wave function is a real physical object that lives in a space with more dimensions than there are atoms in the universe. You accept that every particle is connected to every other particle through that wave, with correlations that propagate in zero time. You accept that the apparent separateness of objects is an illusion, a three-dimensional projection of a higher dimensional reality, whose actual structure you can never directly perceive. There is another cost that rarely gets discussed. In Bohm's framework, the pilot wave determines the velocity of each particle based on the configuration of all particles. This means that if you perturb one particle, even by the smallest possible amount, the wave changes, and the velocities of every other particle in the universe change with it. The universe in Bohm's picture is not a collection of independent things that interact through forces. It is a single, indivisible, interconnected whole. The correlations are not mediated by any signal. They just are. They are the structure of the pilot wave itself. Bell accepted this cost. He thought it was the most honest option. He said on multiple occasions that the pilot wave theory was the only interpretation of quantum mechanics that took the theory seriously as a description of reality, rather than hiding behind words like complementarity and measurement. He was particularly impressed by the fact that Bohm's theory dissolved the measurement problem completely. There was no measurement problem in Bohm's framework. There was no shifty split between the quantum world and the classical world. There was just particles being guided by waves, all the way up and all the way down, coffee cups, planets, galaxies, neurons, photons, all obeying the same equations. I respect that position, even though I'm not sure it is the right one. I think Bell was probably right that Bohm's theory was the most honest available option in the early 1960s. I am less sure he would have stuck with it after the loophole-free Bell test of 2015 and the cosmic Bell test of 2018. The price of the pilot wave, the configuration space wave that connects everything, becomes harder to swallow as the experimental constraints tighten. But Bell's instinct was sound. If you were going to walk through one of the doors, you should walk through it with your eyes open about what it costs. Door 1 says everything is connected. The connection is real. The connection is instantaneous. The connection lives in a space you cannot see, in dimensions you cannot count, in a wave you cannot detect except through its consequences. The price is the separateness of the world you have been experiencing since you were a child. The reward is that the chair you're sitting on still exists when nobody's looking at it. Each door costs something. Door 1 costs the loneliness of the world. The universe in Bohm's picture is, for better or worse, one thing. Part 8. Door 2. The world that is not there when you look away. The second door is the one that is, technically, still the default position of most physics textbooks. The second door is Copenhagen, taken seriously. The second door says you do not have to accept non-locality, because the property that was supposed to be non-locally correlated was never there to begin with. The cost of door 2 is that you give up the reality of properties when nobody's observing them. You give up the chair when no one is sitting on it. You give up the moon when no one is looking. Strictly interpreted, the Copenhagen view says the wave function is not a description of a real thing out there in the world. It is a tool. It is a calculation device for predicting the probabilities of measurement outcomes. Before you measure a photon's polarization, the photon does not have a polarization. It is not that you do not know the polarization. It is not that the polarization is hidden from you. There is no polarization to know. The property does not exist until the measurement creates it. The measurement is not a window onto a pre-existing fact. The measurement is the moment the fact is brought into being. Einstein could not accept this. The famous moment is the one I mentioned in part 1, the moment Pais recorded in his biography. They were walking together at Princeton one evening, in the years before Einstein's death in 1955. Einstein stopped, turned to Pais, and asked, "Do you really believe the moon exists only when you look at it?" The question was not rhetorical. Einstein was actually asking. He was trying to understand whether the Copenhagen interpretation required him to accept that macroscopic objects had no definite reality unless someone was watching them. The Copenhagen answer, strictly interpreted, is yes. Or, more precisely, the question is not well posed. You cannot ask about properties independent of measurement context. The concept of the moon existing when nobody is looking is, in the strictest Copenhagen reading, not false. It is undefined. The moon exists when you look. Looking is all there is. Now I want you to feel what this means. You're sitting somewhere right now. There is a chair beneath you, or a couch, or a bed. You believe it has a definite shape, position, and mass, whether or not you are observing it. You believe that if you closed your eyes, the chair would still be there. This belief is so fundamental to your experience that questioning it feels absurd. The Copenhagen interpretation, applied with full seriousness, says this belief is wrong. The chair, at the deepest level, is made of atoms. The atoms are made of electrons and nuclei. The electrons in the chair, when nobody's interacting with them, do not have definite positions. They are smears of possibility. When you look, or when any measurement-like interaction happens, the smears collapse into definite states. There is an obvious objection. The chair is being measured all the time. Air molecules are bumping into it. Photons are bouncing off it. The Copenhagen response is that those interactions count as measurements. The chair is being measured continuously by its environment, which is why it appears to have definite classical properties. But this response opens a deeper problem. If interactions with the environment count as measurements, where does the line get drawn? At what scale does the quantum smear collapse into classical definiteness? Does a single air molecule count? A photon? A bacterium? Bell, in his final paper, attacked exactly this point. He argued that the word measurement should not appear in any fundamental formulation of physics. It is too vague, too human-centered, too dependent on an undefined boundary. Bell called this boundary the shifty split. It moves. It depends on how you set up the problem. It is not a feature of the physics. It is a feature of the storyteller. The standard modern attempt to fix this is called decoherence, the process by which quantum superpositions become entangled with their environment and effectively become classical. The work of H. Dieter Zeh in 1970 and Wojciech Zurek through the 1980s established that when a quantum system interacts with a sufficiently complex environment, the interference between different branches of the system's wave function becomes undetectable. The cat is constantly being measured by its own metabolism, by the air, by the box. The superposition decoheres long before you open the box. But decoherence does not solve the measurement problem. It explains why you do not see superpositions in practice. It does not explain why there is a single definite outcome at all. In the decoherence picture, the wave function still contains both branches. You just only ever experience one of them. Where the other branch goes is exactly the question many worlds will ask in door 3. Copenhagen, taken strictly, does not have a clean answer. Bell made this point with a precision that I find almost painful. He said that if a fundamental physical theory requires the word measurement to function, then physics does not understand what it is describing. The act of writing this argument as his final published paper in Physics World in August of 1990, weeks before he died, tells you something about the kind of intellectual honesty he possessed. He could have spent his final years accepting awards. The Royal Society had given him the Hughes Medal. He had received the Dirac Medal and the Heinemann Prize. He could have gone on the lecture circuit and given comfortable talks about how marvellous quantum mechanics is. Instead, he used his last published words to attack the foundations of the standard interpretation. He had spent his career arguing that the measurement problem was real, and that the profession was pretending it was not real because the profession had decided not to look. With his last paper, he refused to stop pulling at that thread. I want to come back to Einstein's moonlight question, because the question changes after you have walked through door 2. Einstein asked Pais in Princeton, in the years before his death, "Do you really believe the moon exists only when you look at it?" When Einstein asks the question is indignant. He is angry. He thinks the answer is so obviously yes, of course the moon exists, that anyone who says otherwise is making a category mistake. The question is rhetorical in his mouth. He expects Pais to agree with him. When you ask the question, after walking through door 2, the question is not indignant. It is quiet. It is the kind of question you ask yourself in a hotel room at 3 a.m. when the world feels less solid than usual. Do you really believe the moon exists only when you look at it? The Copenhagen answer is, strictly, yes. The question becomes, can you live with that answer? Can you go through your daily life knowing, in the back of your mind, that the world you experience as solid and persistent and independent of your attention is, at the deepest level, a structure that depends on observation for its very existence? Some people can. Some physicists have made peace with door 2 and walk through it daily and find it tolerable. They say, the math works, the predictions are exact, the world I experience is the world I experience, and whatever quantum mechanics is doing at the deepest level is the quantum mechanics business. This is in many ways the descendant of the shut up and calculate attitude. It is not unreasonable. It is one of the things you can do when you stand in front of door 2 and try to walk through it. But Bell could not. Bell looked at the door and saw that the shifty split it required was not actually defined anywhere. He looked at it for 40 years. He never accepted that the measurement problem was a curiosity. He thought it was the central crisis in the foundations of physics, and his final published paper said so. If Dr. 2 is going to be a real door, somebody needs to actually define what counts as a measurement, and nobody has done that in 100 years, and Bell did not believe anyone was going to. The door is, in a real sense, half-built. You can walk through it, but you walk through into a corridor that has not yet been finished, and nobody is sure how to finish it. That is what door 2 costs. The chair you're sitting on, the screen you're watching, the room around you, the air you breathe, the body you wear, all of it, at the deepest level, has no definite properties unless something is watching. The shifty split between the watched and the unwatched is undefined. You're standing in a world whose existence depends on observation in a way that nobody has been able to make precise. The mathematics that describes your daily experience is the mathematics of a measurement process whose definition is unfinished. Welcome to door 2. Part 9. Door 3. The branching of you. The third door was proposed by a 26-year-old PhD student at Princeton in 1957. His name was Hugh Everett III. His thesis advisor was John Archibald Wheeler. The thesis was the most radical interpretation of quantum mechanics ever proposed, and it was also, in a particular sense, the most conservative. It made the smallest possible modification to the theory. It just refused to add anything to the Schrödinger equation. It said, in effect, the Schrödinger equation is universal. It applies always to everything without exception. There is no special role for measurement. There is no wave function collapse. The equation just keeps running, forever, for everything. The consequence of this small refusal is enormous. If the Schrödinger equation applies universally, and if there is no collapse, then when you measure a photon's polarization, both possible outcomes happen. The measurement entangles you with the photon. After the measurement, the universal wave function contains a branch in which you saw vertical polarization and another branch in which you saw horizontal. Both branches are real. Both versions of you are real. They cannot communicate because the branches decohere. They become orthogonal in the wave function, and the interference between them becomes effectively impossible to recover. From inside one branch, the other branch is invisible. You experience the single definite outcome you experience. But the other outcome is, in this picture, still happening in another branch. This is many worlds. The name was not Everett's. He called the framework the relative state formulation. The name many worlds came later, popularized by Bryce DeWitt in the 1970s. But the structure is the same. Every quantum event, every photon interaction, every radioactive decay, every measurement-like process branches the universal wave function. The branches multiply. After a sufficient amount of time, the number of branches is unimaginably large. There are versions of you in some branches who became a doctor instead of whatever you became. There are versions of you in other branches who never existed because some 20th century event went slightly differently. The branches are all, in this picture, equally real. Your sense that there is one of you, with one biography, is a perspective, not a fact. From inside any single branch, the branch you're in feels like the only one. But the wave function contains, in principle, all of them. Wheeler, when Everett brought this thesis to him, made him cut it from 137 pages to a thin 27-page version that removed most of the philosophical implications. The full version was not published until decades later, after DeWitt's popularization had created an audience for it. Bohr's associate Leon Rosenfeld was actively hostile. When Everett visited Copenhagen in 1959, hoping to discuss his ideas with Bohr directly, the reception was cold. Rosenfeld later described many worlds as theology, which in physics is not a compliment. Everett never got an academic physics position. He went into military operations research. He worked at the Pentagon's Weapons Systems Evaluation Group, doing analyses of nuclear war scenarios. He moved to the Institute for Defense Analysis. He became wealthy from defense contracting. He also became an alcoholic and a heavy smoker. He died of a heart attack on July 19, 1982, at the age of 51. His daughter Elizabeth, who struggled with mental illness, took her own life on June 24, 1996. In her note, she expressed the hope of ending up in the same parallel universe as her father. There is something I find unbearable about that note. The man who proposed that the universe splits into infinite branches every time anything happens was himself split apart by the profession's inability to take his idea seriously. He spent his life in a career that had nothing to do with the question that obsessed him as a graduate student. He drank. He died young. His daughter wrote a note that read like a prayer to her father's own theory. It was as if many worlds, the interpretation, became a kind of haunting that followed his family through 3 generations. Now, is many worlds correct? I have to be careful here, because the answer depends on what you think interpretation means. Mathematically, many worlds is the cleanest of the 4 doors. A 2019 analysis by Howard Wiseman's group, published in Nature Physics Volume 16, page 1199, made the logical structure explicit. Bell's theorem, the paper showed, rests on 3 formal axioms: local causality, no superdeterminism, and one world. Accept the first 2, and you are logically compelled to accept the negation of the third. You're compelled to accept many worlds. The structure of the argument is the same as the structure of Bell's original theorem. It is a mathematical implication, not a preference. So if you do not want to give up locality, and you do not want to give up free choice, many worlds is forced on you. The cost of door 3 is the existence of an infinite number of equally real branches of the universal wave function. The cost is that the singular sense of self you have, the feeling that there is one you with one biography making one set of choices, is a feature of being inside a single branch. From the perspective of the universal wave function, there is no single you. There are many. The technical problem with many worlds is the meaning of probability. In standard quantum mechanics, when you measure a photon's polarization, you say there is a 50% probability of vertical and 50% of horizontal. The probabilities reflect your uncertainty about the outcome. But in many worlds, both outcomes happen, every time. There is no uncertainty. So what does probability mean? Why does the experience of being in a branch correspond statistically to the Born rule? Several proposed answers exist. David Deutsch and David Wallace at Oxford have argued that the Born rule emerges from rationality considerations applied to agents inside the branching framework. Lev Vaidman has argued for a self-locating uncertainty interpretation in which probability reflects an observer's uncertainty about which branch they will find themselves in after a measurement. None of these attempts has produced a consensus solution, but step back from the technical problem for a moment, because the existential cost of door 3 is what I want you to actually feel. If many worlds is correct, then your life, the life you experience as singular and unique and yours, is one infinitesimally thin slice of an unimaginably vast multiverse. Somewhere, in some branch of the universal wave function, there is a version of you who made a different choice an hour ago. There is a version of you who took a different job at 22. There is a version of you whose parents never met. There is a version of you who died at age 14 of an illness you did not have in this branch because the radioactive decay that would have given you cancer went the other way. There is a version of you who is happier than you are. There is a version of you who is in more pain than you are. All of them are real. All of them are experiencing their lives as singular and unique and theirs. The singularity of your experience, the feeling that this life is the life, is, in this picture, a perspective. From the inside of any branch, the branch you are in feels like the only one, but the wave function contains all the branches. I do not know how to make this feel emotionally tolerable. I am not sure it is supposed to feel tolerable. The most rigorous mathematical interpretation of quantum mechanics, the one whose price is just the universality of the Schrödinger equation, demands that you accept an infinite proliferation of versions of yourself. Some physicists I respect find this strangely comforting. Sean Carroll, who has written one of the best popular accounts of many worlds in his book Something Deeply Hidden, has said that many worlds is the most parsimonious interpretation because it adds nothing to the math. The branches are already there in the wave function. Many worlds just refuses to delete them. Carroll finds the idea of infinite branches less troubling than the idea of wave function collapse, which he sees as an ad hoc addition with no clear physical mechanism. Other physicists find many worlds intolerable. They cannot live with the idea of infinite versions of themselves. They prefer the price of non-locality or the price of anti-realism to the price of branching. The interpretive community is genuinely divided. The 2013 survey by Schlosshauer, Koffler and Zeilinger found Copenhagen support at about 42%, many worlds at about 18%, objective collapse at 9%, the rest scattered across pilot wave, cubism, relational quantum mechanics, and consistent histories. A 2024 update showed Copenhagen dropping toward 36%, and many worlds rising toward 24%. Sean Carroll has called the standard chart of these positions the most embarrassing graph in modern physics. He is not wrong. The chart is the visible signature of 40 years of professional silence around the most important question in the field. The 4 doors are still open. Door 3 is one of them. Door 3 asks you to accept that you are not singular. The reward is the cleanest mathematical interpretation available. The Schrödinger equation runs forever. There is no shifty split. There is no spooky non-local connection. There is just branching, all the way down, with versions of you in all the branches, experiencing their own particular branches as the only branch that exists. If you can swallow that price, door 3 is the most internally consistent of the 4. If you cannot, you have to stand in front of another door. Part 10. Door 4. The clockwork at the beginning. The 4th door is the one almost nobody talks about, and it is the one that, when you understand it fully, should disturb you the most. The 4th door is superdeterminism, and I want to be careful about how I describe it, because the word determinism on its own sounds almost reasonable. You might think, well, maybe the universe is deterministic. Maybe classical physics was right about that part. Superdeterminism is not that. The assumption in Bell's theorem that rarely gets examined is called measurement independence. The assumption says that the experimenter's choice of what to measure is statistically independent of the hidden variables that determine the outcome. In plain language, the assumption says that the experimenters are free to choose their detector settings, and that those choices are not correlated in any deep cosmological way with the properties of the particles being tested. Superdeterminism rejects measurement independence. It says that the settings of the detectors and the hidden variables of the particles are correlated. Not by signal, not by conspiracy, by initial conditions, by the way the universe was set up at the beginning. I want to make clear how radical this is. Ordinary determinism says that the laws of physics determine what happens next, given what happened before. It is the picture Laplace gave us. If you knew the state of the universe at one moment and knew the laws, you could predict every future event. Superdeterminism is not that. Superdeterminism says that the initial conditions of the universe, at the moment of the Big Bang, were arranged in such a way that every experimental test of Bell's inequality, ever in the entire history of the universe, happens to produce exactly the correlations predicted by quantum mechanics. Not because the universe is actually quantum mechanical, because the initial conditions were fine-tuned to mimic quantum correlations for every possible experiment any conscious being could ever perform, at every scale, at every location. The initial conditions had to know, in some sense, what experiments humans would perform 13.8 billion years later, and they had to be arranged to produce the right fake results for every one of them. That is not a physical mechanism. That is a conspiracy theory about the beginning of time. Bell coined the term superdeterminism in a 1985 BBC radio interview with the physicist Paul Davies. He said there is a way to escape the inference of superluminal speeds and spooky action at a distance, but it involves absolute determinism in the universe, the complete absence of free will. He then added, "Suppose the world is superdeterministic. Not only is what happens at one detector determined by the initial conditions of the universe, but what the experimenter does at that detector is also determined. In that case, the experimental result is no longer a fair sample of what would have happened under different conditions." Bell raised the possibility, but he did not endorse it. He saw it as the price of escaping non-locality, and he believed the price was too high. Some modern physicists have argued otherwise. Gerard 't Hooft, the Dutch Nobel laureate, has advocated for superdeterminism through what he calls the cellular automaton interpretation of quantum mechanics. He published a book-length treatment in 2016 as Springer Fundamental Theories of Physics, Volume 185. He proposes that quantum mechanics arises from a deterministic cellular automaton operating at the Planck scale. The apparent quantum behavior we see at our scale is a coarse-grained statistical view of the underlying deterministic clockwork. Bell's theorem, in this picture, is consistent with locality because the assumption of measurement independence is wrong. Sabine Hossenfelder is the most vocal contemporary proponent. She has argued, in a 2020 paper in Frontiers in Physics Volume 8, page 139, that the standard objections to superdeterminism are ill-founded. She has called the concept of free will, in her words, logically incoherent nonsense. Her position is that the entire question of free choice is a holdover from outdated philosophy, and that the universe has always been a clockwork, and that Bell's theorem only seems strange because we were attached to the idea that we made real choices about what to measure. But here is why most physicists reject superdeterminism, and why I think they are right to reject it, at least until somebody produces a specific physical model with the right structure. Superdeterminism does not just sacrifice free will. It sacrifices the entire enterprise of experimental science. If the settings of detectors are correlated with the properties they measure, then no experiment can ever be trusted. You cannot test any theory because the universe might have arranged the initial conditions to produce misleading results. Shimony, Horn, and Clauser wrote in a 1976 paper that unless we proceed under the assumption that hidden conspiracies of this sort do not occur, We have abandoned in advance the whole enterprise of discovering the laws of nature by experimentation. Zeilinger has his own version. He has said that if measurement settings were determined in advance, then it would make no sense at all to ask nature questions in an experiment, since then nature could determine what our questions are. And the cosmic bell tests have pushed the super-deterministic correlation back to the very limits of observational cosmology. In February of 2017, a collaboration including Anton Zeilinger, David Kaiser at MIT, and Alan Guth at MIT published results from the first cosmic bell test. Instead of laboratory random number generators, they used light from Milky Way stars approximately 600 light-years away. The colour of each incoming stellar photon, red or blue, determined the measurement setting. The Bell inequality was violated by more than 7 sigma and 11 sigma in 2 separate configurations. Any hidden common cause between settings and outcomes would have to have been established at least 600 years ago, before the starlight was emitted. Then, on January 11, 2018, at the Observatorio del Roque de los Muchachos on La Palma in the Canary Islands, the same collaboration went further. The Telescopio Nazionale Galileo, with its 3.58-metre mirror, was pointed at one high redshift quasar. The William Herschel telescope, with its 4.2-metre mirror, was pointed at a different quasar in the opposite direction of the sky. The light from these quasars was emitted 7.8 billion and 12.2 billion years ago. That light, billions of years old, was used to choose the detector settings in real time. I want you to appreciate the ambition of this. The 2 domes opening to the cold high-altitude night air on La Palma, the telescopes locking onto opposite quasars whose light left its source before the Earth was a coherent body. The photons that chose the detector settings had been travelling through space since before the Sun formed, since before our galaxy had finished assembling itself. If there is some cosmic conspiracy rigging the experiment, it would have had to be set in motion when the universe was a small fraction of its current age. The experimenters were literally reaching back through cosmological time to ensure that their choices were as free as anything choice can be inside a universe with a finite past. Over 30,000 entangled photon pairs were measured. The Bell inequality was violated by 9.3 sigma. The p-value was less than 7.4 times 10 to the minus 21. The result excluded any local realist influence mechanism from 96% of the space-time volume of the pass-like cone of the experiment, from the Big Bang to the present. If there is a conspiracy, it was established within the first 4% of the age of the universe, less than 600 million years after everything began, and in May of 2018, the results of the Big Bell test were published in Nature Volume 557, page 212. Approximately 100,000 human volunteers across the world played an online video game designed to produce genuinely unpredictable binary choices. A machine learning oracle tried to predict each player's next input, incentivizing truly random behavior. The participants generated more than 97 million binary choices in 12 hours on November 30th, 2016. Those choices were routed in real time to 13 different experiments on 5 continents, using photons, atoms, atomic ensembles, and superconducting devices. All 13 experiments violated Bell's inequality by more than 8 standard deviations. 100,000 human beings, actively trying to be unpredictable, freely choosing in real time. And the universe still refused to be locally real. Whatever was going to happen in those 13 laboratories was going to happen regardless of which combination of free choices the volunteers made. Superdeterminism, if you want to defend it after these results, has to be the claim that the initial conditions of the universe correlated the genetic predispositions, the life experiences, the cognitive states, and the moment-by-moment moods of 100,000 people across 5 continents with the polarizations of photon pairs in 13 distinct laboratories. That is the conspiracy that has to be true if door 4 is the right door. There is a final turn of the screw, and I want to mention it because it is one of the most elegant results in this whole field. In 2006, the mathematicians John Conway and Simon Cochin at Princeton published what they called the free will theorem in Foundations of Physics, Volume 36, page 1441. They proved, using 3 axioms, one about quantum predictions for spin measurements, one about entangled particles, and one about the finite speed of information propagation, that if experimenters have free will, in the sense that their choices are not determined by prior information available to the particles, then the particles' responses are also not determined. The particles, in a precise mathematical sense, have free will too. Conway reportedly said, "It is not about theories anymore. It is about what the universe does. A particle has a choice." Their strong free will theorem in 2009, in the notices of the AMS Volume 56, page 226, weakened the assumptions even further. The implication is a symmetry. If you deny free will to the experimenters, you deny it to the particles. If you grant it to the particles, you grant it to the experimenters. You cannot selectively eliminate freedom from one side of the experiment. Either both sides have it, or neither side has it, and if neither side has it, then the entire enterprise of experimental science, the enterprise of asking nature questions and accepting nature's answers, becomes a kind of theatrical performance in which both questioner and respondent are reciting lines that were written before the universe began. I want you to imagine for a moment standing in a circular room with 4 doors. Each door is open. Each door leads somewhere. Door 1 leads to a universe where everything is touching everything else through a wave in a space you cannot see, in dimensions you cannot count. Door 2 leads to a universe where the room you are standing in becomes formless when you close your eyes, and there is no defined moment at which the formlessness becomes form again. Door 3 leads to a corridor with an infinite number of versions of you walking down an infinite number of corridors, each one slightly different. Door 4 leads to a clockwork in which the act of reaching for the doorknob was already mapped at the Big Bang 13.8 billion years ago by initial conditions that knew, somehow, that you would reach for that particular handle at this particular moment. There is no 5th door. The mathematics will not permit one. You have been standing in this room since 1982. Most people watching this were never told the room exists. You do not have to choose tonight. You do not have to choose any night. But the 4 doors will not go away. They have been open for 40 years, and the data has only gotten stronger. The room is real. The doors are real. And the price each door costs is real. We will get to one more deep question before this story closes, and it is the question about why the universe stops where it stops. Because even the 4 doors do not exhaust what the data says. There is one more limit, deeper than the 4 doors, that nobody has been able to explain. Part 11. The limit nobody can explain. Here is something that I think gets lost in most popular treatments of Bell's theorem. The 4 doors I just walked you through are the doors that the mathematics requires. But the mathematics also has a deeper structure, and the deeper structure has a question hidden inside it that nobody has been able to answer. I want to take you back to the numbers. Local realism allows the correlation parameter S to be at most 2. Quantum mechanics, by aspects measurement and by every subsequent experiment, allows S to reach approximately 2.828, which is 2 times the square root of 2. The Sorelson bound, named after Boris Sorelson, who proved this exact result in 1980, in a paper in Letters in Mathematical Physics Volume 4, pages 93 through 100, is 2 times the square root of 2. That is the absolute mathematical maximum for quantum correlations. It is not an experimental approximation. It is an exact upper bound that Sorelson proved from the structure of Hilbert's space and the rules of quantum mechanics. But here is the part that should make you stop. 2 times the square root of 2 is not the algebraic maximum of S. The algebraic maximum is 4. You could imagine theories where S reaches 4. Such theories exist. They were proposed by Sandu Popescu and Daniel Rohrlich in 1994 in Foundations of Physics Volume 24, page 379. They are called no-signaling theories because they obey the constraint that you cannot send information faster than light. The Popescu-Raulich box is a hypothetical device that achieves S equals 4. It exists mathematically. It just does not exist physically. Nothing in the universe has ever produced correlations stronger than 2.828. So the hierarchy goes like this. Local realism allows S up to 2. Quantum mechanics allows S up to about 2.828. General no-signaling theories allow S up to 4. Quantum mechanics sits in the middle, and the middle is deeply strange if you stop to think about it. Quantum mechanics is more non-local than classical physics, but it is less non-local than it could be while still respecting special relativity. Something is constraining the universe. Something stops the correlations at 2.828 and refuses to let them get any stronger. We can measure that constraint. We can calculate it. We cannot explain it. This is sometimes called the Cyrilson question. Why does nature stop where it stops? Why does the universe pick this particular ceiling out of the much larger envelope that relativity allows? Several proposals exist. The most interesting is the principle of information causality, proposed in 2009 by Marcin Pawłowski and his collaborators in Nature Volume 461, page 1101. The principle is, roughly, that no party can gain more information about another party's database than the number of classical bits transmitted. It turns out, mathematically, that information causality picks out exactly the Cyrilson bound. The universe is non-local, but it is not so non-local that information can be gained for free. A different proposal, by Tobias Fritz and collaborators in 2013, in Nature Communications Volume 4, page 2263, called local orthogonality, also yields the Cyrilson bound. None of them has produced a consensus. The universe has a speed limit for light. It also has a non-locality limit for correlations. We have a theory of relativity that explains the first. We do not have a comparable theory for the second. We can prove it from the structure of quantum mechanics. We cannot explain it from anything deeper. This is, in many ways, the deepest open question in the foundations of physics that you have probably never heard of. The four doors get most of the attention because they are dramatic. The Cyrilson question is quieter, but it is, I think, more important. The doors are about the consequences of the violation. The Cyrilson question is about the structure of the violation itself. There is one more piece of the structure that deserves mention, and it is the retrocausality program. I see, all over the internet, the claim that quantum eraser experiments prove the future can change the past. This is a misreading. The quantum eraser experiment in its classic form by Kim, Yu, Kulik, Shi, and Scully in 2000, in Physical Review Letters, Volume 84, page 1, is fully explained by post-selection. When you look at the total pattern of detections without sorting the signal photons by what happened to their idler photon partners, there is no interference pattern. The interference appears only when you sort. That sorting is a classical operation performed after the fact. No information travelled backward in time. The real case for retrocausality is more subtle. It comes from the work of the philosopher Hugh Price at Cambridge and the physicist Ken Wharton at San Jose State. They argue that Bell violations should be understood as evidence for time-symmetric hidden variable theories, in which future measurement settings genuinely constrain past hidden variable states. This is distinct from superdeterminism. It allows free will. The experimenters genuinely choose. The choices then propagate backward in time through the hidden variable structure of the system. Price wrote to Bell about this in 1988. Bell wrote back. He said that when he tried to think about backward causation, he lapsed quickly into fatalism. He did not endorse it. He did not rule it out. Retrocausality is more interesting and more serious than it gets credit for. It is a foundational program with a small but real research community. If somebody produces a specific retrocausal model that reproduces the predictions of quantum mechanics, with the loophole-free tests and cosmic Bell tests respected, and the Cyrilson bound naturally emerging, then it becomes a genuine fifth interpretive position. No such model exists yet. But the work is being done, by people who have been carrying Bell's instinct forward into the next generation. So the picture, when you step back, is this. The 4 doors are the rigorous interpretive options that the data demands. The Sirelson question is the deeper structural mystery underneath the doors. The retrocausality program is the most credible candidate for a future framework that might give us a different way of understanding the violation. Underneath all of it, the experimental result is unchanged. The number is still 2.697. The number has been confirmed by every experiment performed in the 43 years since Aspect first measured it. The number has been pushed toward 2.828 in optimized modern experiments. The number has been confirmed by transition edge sensors in the sub-basement of the Hofburg Castle in Vienna. The number has been confirmed by nitrogen vacancy centers in Diamond, 1.3 kilometers apart, under the Delft University campus. The number has been confirmed by quasar light from 12.2 billion years ago. The number has been confirmed by 97 million binary choices from 100,000 human volunteers across 5 continents. The number does not move. The result does not move. The interpretation is the only thing that is still in motion, and the interpretation has been in motion for 43 years, and it is still in motion now, and it may be in motion for many more years before the field, taken as a whole, settles on a position the experimental data has been pointing at since before most of you watching this were born. Part 12. The silence that was left behind. I want to come back to the silence because the silence is, in many ways, the deepest part of this story. The strangest thing about Bell's theorem is not the theorem itself. It is what happened after the theorem was proven. It is what did not happen. The 2022 Nobel Prize was awarded to Alan Aspect, John Clauser, and Anton Zeilinger on October 4, 2022. The citation said, "Experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science." Those last 3 words, quantum information science, are doing enormous work. The Nobel Committee recognized what you can do with entanglement. It did not address what entanglement tells you about reality. The press release discussed qubits and quantum computing and quantum cryptography. It did not mention non-locality. It did not mention the measurement problem. The profession has learned to profit from the phenomenon while continuing to avoid what it implies. Shut up and calculate, but now with venture capital and stock options. I think Bell would have had something sharp to say about this. He spent his life arguing that the measurement problem was not a philosophical curiosity, but a genuine crisis. I think he would have been pleased that the experimentalists were finally recognized. I think he would have been exasperated that the recognition came framed as technology rather than as truth. But I think he would have also smiled, that quiet Belfast smile, because the theorem had, in the end, won. The data was in. The question he had asked could no longer be avoided. It could only be deferred, and deferral has a shelf life. At the Nobel ceremony in Stockholm, Aspect spoke first. His words were precise. He said, "That recognition should go first to the late John Stuart Bell, without whom we would not be here today." He told the permanent position story to the Nobel audience. He told them about the meeting at CERN in 1975, about Bell's first question, about the crackpot warning. And then Aspect moved on, and the ceremony continued, and the world went home to whatever world it was already in. I want to do something the Nobel Committee did not do. I want to count the cost. David Bohm died in a London taxi on October 27, 1992, 75 years old, heart attack. He had spent 40 years watching the physics establishment ignore the pilot wave theory he'd constructed in São Paulo. He had recovered his United States citizenship in 1986 after a lawsuit. He never received the Nobel. The interpretation that Bell would call the most honest version of quantum mechanics is still taught in most physics departments as an oddity, a footnote. He was right too early. The cost of being right too early was to be ignored by the profession until he died in a country that was not his home, in a city that had not chosen him, in a cab on a road he had not asked to be on. John Stuart Bell died of a cerebral hemorrhage on October 1st, 1990 in Geneva. He was 62 years old. His wife Mary, also a physicist at CERN, survived him. The MacTutor Archive at St Andrews and Physics World magazine both report that he had been nominated for the Nobel Prize that year. The records are sealed until 2040. We may never have formal confirmation, but the awards he received in his final years, the Hughes Medal from the Royal Society, the Dirac Medal, the Heinemann Prize, honorary degrees from Queen's and from Trinity College Dublin, tell you what the community had finally figured out. He died weeks before what many believed would have been his Nobel cycle. His final paper, Against Measurement, had appeared in Physics World in August of 1990, weeks before his death. He was challenging the profession's most sacred concept with his last published words. That was Bell. He could not stop pulling at threads, even when nobody wanted to see what unravelled. The most important theorem in the history of science had been proven in his evenings and on his holidays, in a dead trilingual journal, and the man who proved it never lived to see the loophole-free experiments that confirmed it beyond any conceivable doubt. John Clauser performed the first experimental Bell test in a Berkeley basement with no funding. He was rewarded by being thrown out of Feynman's office. He never held a tenured professorship. He waited 50 years for his Nobel. He was 80 when the call came. He had actually expected the experiment to prove quantum mechanics wrong. When the universe told him otherwise, he accepted it and published. The profession punished him for it for half a century. Alain Aspect was warned by Bell himself that a majority of physicists would consider him a crackpot. He spent 5 years building an experiment the profession did not want. The result was met with indifference in 1982. He waited 40 years for his prize. At the ceremony, his first words honoured the dead man who made it all possible. Abner Shimoni, who co-derived the CHSH inequality and made Bell's theorem experimentally testable, died in 2015, 7 years before the prize. Hugh Everett III proposed many worlds at 26. The establishment's response was so hostile that he abandoned physics. He went into military operations research, became an alcoholic, and died at 51. His daughter took her own life 4 years later. Stuart Friedman, Clauser's graduate student in the Berkeley sub-basement, died in 2012, a decade before the Nobel. Greta Hermann identified the flaw in von Neumann's impossibility proof in 1935, the same year EPR was published. The physics community ignored her work for 40 years because she was a woman publishing in a journal that physicists did not read. By the time Bell independently rediscovered her insight, she had been dead for 19 years. That is the record. That is what the physics community did to the people who dared to ask what quantum mechanics means. And here is the final bitter irony. Bell's theorem, which was ignored as philosophy for decades, which was treated as professionally disreputable, which cost the people who worked on it their careers, now underpins a multi-billion-dollar global industry. Quantum computing, quantum cryptography, quantum teleportation. Every piece of it traces directly to Bell's 1964 paper and the experiments that confirmed it. Arthur Eckert's 1991 E91 protocol, which launched practical quantum cryptography, is based directly on Bell's inequality. If an eavesdropper intercepts the photons, the Bell violations disappear, and the parties know the key is compromised. The security guarantee is the violation itself. IBM, Google, IonQ, Quantinuum, PsiQuantum, the European Union's EuroQCI initiative, China's MOSI quantum satellite, the United States National Quantum Initiative, all of it rests on the entanglement that Bell proved cannot be explained away, and that Aspect proved is real. The thing the profession called a distraction is now its most commercially valuable product. The people the profession punished are now the field's founding figures. I want to close on what the result actually means for the world the listener is in. The universe is not locally real. That is not a theory. That is not a hypothesis. That is not an interpretation. That is what the data says. It has been saying it since 1982. And most of you watching this were never told. The picture of reality that science has been working with for 300 years, the picture of separate objects with definite properties influencing each other only through local interactions, is false, not approximately false, not false in some exotic regime of extremely small particles or extremely high energies, false in principle, false at every scale, false for every particle. The entangled photons in Aspect's basement laboratory in 1982 do not respect locality any more than the entangled ions in trapped ion experiments today, any more than the entangled nitrogen vacancy centers in Hansen's diamonds 1.3 kilometers apart in Delft, any more than the entangled photons in the Hofburg Castle in Vienna. The violation is the same. The universe does not become locally real when you zoom out. It was never locally real to begin with, and this is not something that only applies to carefully prepared laboratory states. Entanglement is everywhere. Every interaction between any two quantum systems produces it. Every photon that bounces off your skin and reaches someone's eye creates entanglement between you and the photon. Every breath you take entangles the molecules of air with the molecules of your lungs. The reason you do not notice this is not that entanglement is absent. It is that decoherence, the interaction with the environment, scrambles the quantum correlations so rapidly that they become undetectable. But undetectable is not the same as non-existent. The universe is saturated with entanglement. The violation of a local realism is not a laboratory curiosity. It is the default condition of all matter at all times at all scales. You're living in a universe that is not locally real, and you always have been. The only reason it feels locally real is that your senses are too coarse to detect the entanglement that permeates everything around you. That is what Aspect measured in the basement at Orsay in 1982. Not an exotic quantum phenomenon, the fundamental character of reality, stripped of the decoherence that usually hides it from view. Aspect once said, "Mostly nobody cared." That sentence, in its original setting, was an observation about the indifference of the physics community in 1982. The community heard the result, decided it was an interpretive curiosity, and went back to using quantum mechanics for other things. The people who did the work, Bell, Bohm, Clauser, Aspect, Shimoni, Herman, Everett, paid the cost of that indifference, year by year, in withheld recognition and shortened careers and lost time. They paid it because nobody else was going to. When Aspect says mostly nobody cared, he is describing a profession that turned its head. But by the time you have walked through the 4 doors with me, the same words land differently. The reason mostly nobody cared was that mostly nobody had been told what the result meant. The result meant that the separateness of distant things is the surface of an ocean. The result meant that the chair you're sitting on may not have a definite shape when nobody's looking. The result meant that there may be other versions of you experiencing other versions of this exact moment in branches that decohered from this one a long time ago. The result meant that the choice you feel you are making right now to keep listening or to look away may have been mapped at the moment of the Big Bang, in initial conditions that already knew what every choice was going to be. The 4 doors do not lead out of this, they lead deeper. Do you really believe the moon exists only when you look at it? When Einstein asked the question, in Princeton, in the last years of his life, he asked it indignantly. He expected the answer to be obvious. The answer was supposed to be yes, of course the moon exists. The question was supposed to be a reductio against an interpretation that demanded otherwise. When you ask it, after the 4 doors, the question is not indignant. It is quiet. The Copenhagen answer is strictly yes. The Bohmian answer is the moon exists, but it is connected to everything else in a configuration space that has more dimensions than the universe has atoms. The many worlds answer is the moon exists in every branch where it exists, and you only see the moon you see because you are in this branch. The superdeterministic answer is the moon exists, and your looking at it was already mapped at the beginning of time. There is no 5th answer. The number is 2.697. 40 standard deviations above the limit that local realism was supposed to obey. confirmed by transition edge sensors in the sub-basement of the Hofburg Castle, confirmed by nitrogen vacancy centers in Diamond 1.3 kilometers apart, confirmed by quasar-light 12.2 billion years old, confirmed by 97 million free choices from 100,000 human beings on 5 continents. The number has not moved. The number will not move. The universe made up its mind a long time ago. We are just now, finally, reluctantly, starting to listen to what it has been telling us. The universe is not locally real. That is not a theory. That is not a hypothesis. That is what the data says. It has been saying it since 1982, and you are never told what it means.